Okay, so let's review what we learned last time. So last time we still talk about the chemical reactions, but that's not the type of the chemical reaction. We focus on several kind of the chemical reaction. The first one we talk about is a precipitation reaction, which means you're going to have a solids or you're going to have a solids coming out of the aqueous solution. You put originally you put two aqueous solution, which is clear, or maybe a colorless, maybe a clear, maybe color solution, but that's going to be clear solution, right? And then you mix them together, they're going to have some solids coming out. Okay, maybe it's a white solids, maybe it's a black solids, maybe some other color solids, but they have some solids coming out, which is the precipitate. And we did the experiments, right? Lab 990 in the last time. So you see, we have the precipitate, okay? Precipitation reactions. And here, the precipitation reaction, we all talk about the double displacement reactions. The reaction will exchange the cations and making two new compounds. That's it. Okay. And we also talk about the acid-base reaction. And we talk about acid-base reaction. Eventually, it's just the acid, which is the hydrogen ion, is going to react with the hydroxide ion and to making water. And this is the acid-base reactions. Okay, this is the acid-base reactions. Okay, hydrogen ion, which is coming from the acid, hydroxide ion, which come from the base. Those two neutralize together to make water. And this is the acid-base reaction. This is fundamental parts. Okay. And we also talk about the redox reaction. But we only talk about, okay, what kind of redox we talk about is a reduction plus oxidation. The reduction is talking about something decrease, oxidation talking about something increase. And the something here is the oxidation number. Is the oxidation number. And as long as you can figure out the oxidation number in each of the for each of the elements in the compounds, and then you can, based on the chemical reactions, figure out which one is increase, which one is decrease, right? So then you will figure out which one is reduced, which one is oxidized. Okay, yeah. The oxidation number, we made some calculation, right? First is if it's elements, all the elements, pure elements, the oxidation number is O0. Okay, the oxidation number O0. So that means if you have a hydrogen gases is a hydrogen, oxidation number is 0. Nitrogen gases, oxidation number for each of those atoms are 0. And or you talk about the pure copper, the oxidation number is still 0. Pure iron still 0. Okay, as long as it's elements, it's all 0. Okay, so this is by definition. And we talk about iron, that's gonna be equal to oxidation number is just equal to the charge number. Okay, equal to their charge number. Sodium ion, then that's gonna be equal to +1. Chloride ion, the chlorides, that's gonna be -1. So that's why if you look at the formula, sodium chloride, since this is only compound, so the cation and anion is inside. Those guys are cation and anion, so they are charged. So the oxidation number, this one is +1, and this one is -1. Okay, yeah. And we also talk about potassium permanganate. I mean, although you don't know what is the oxidation number for magnesium, but at least you know oxidation number for potassium, right? Potassium is a 1A group, so this is +1. And you will talk about oxidation number for magnesium hydroxide. Well, again, magnesium is an ion, right? The 2A group. So magnesium here is a +2 for the oxidation number. And the other two rules, one is talk about for oxygen. The other one is for hydrogen. Oxygen, we said that's -2. Okay, most of the cases. For the peroxide, it's -1, but for the rest of other cases, it's all -2. Okay, and I'm not going to test you for the peroxide, so you don't have to worry about the peroxide thing. Okay, hydrogen we talk about. I mean, most of the cases is always +1. Okay, most of the cases +1. So that's why we can base on those four rules to figure out the oxidation number for each of the elements, right? Because we talk about the sum of the oxidation number is equal to 0 if it's in a compound, right? For example, like a sodium phosphate. Okay, what is the oxidation number for this? For phosphate. Sodium phosphate is an ionic compound. So the sodium over there should be a cation, right? For the sodium cation, that's going to be +1. So the +1, you times 3, since we have 3 of the sodium, and plus oxidation number for the phosphor, and plus -2 for oxygen, because we know the oxygen is -2. You times 4. Totally, the sum is equal to 0. Okay, the sum is equal to 0. So you can say 3 plus P minus A equal to 0. So obviously P is equal to +5. Make sense, right? Okay. In the polyatomic ion, those in the polyatomic ion, these elements besides the oxygen, the always is positive number. Okay, this guy is always positive. Just like barium sulfate. What is the oxidation number for sulfate? Or barium sulfite. Barium sulfite. What is the oxidation number for this? Again, what is the oxidation number for the sulfate? Sulfur in sulfate. What is the oxidation number for sulfur in sulfite? Again, barium. What is the charge for the barium? Barium in the 2A group, and this is in only a compound, so the charge should be +2. And you know oxygen is -2. This is also +2, this is -2. So just based on the sum equal to 0 and figure out the oxidation number for sulfur. The barium is just a +2 plus sulfur plus -2 times 4. That's equal to 0, which is for that one. That's 2 plus sulfur minus 8 equal to 0. So sulfur should be +6 for the sulfate. Second one, for this one, that's a +2 and plus sulfur plus -2 times 3 equal to 0. Then you see 2 plus sulfur minus 6 equal to 0. So this sulfur is +4. So oxidation number in this sulfur is +4. That's it. Okay, yeah. Okay, so this is what we review. And I would like you to, and by the way, on next Tuesday, we're going to have a quiz. One of the question is talking about how to write the oxidation number, how to calculate the oxidation number for certain elements in the compound. Okay, yeah. Now I would like to review one more thing. for the net ionic equation. So let's turn to the page 15. I will also give you some of the question, the homework for this practice. Okay, let's look at question 3 and 4 for 15. Page 15. Page 15. Yellow study guide. Okay, so let's work on the question 3 and 3. And then you will think about the question number 4. Okay, yeah. I'm going to do the 3 and you're going to do the 4. So this one, 2 HCl aqueous react with well, let's just do 4 and you're going to work on the 5. Okay, since this one is more complicated, we need to predict the reaction first. Again, you see those 2 compounds, those are ionic compounds. This is another ionic compound. So the first thought is what kind of reaction it is. So if you have to think about, realize what kind of reaction it is, and then you can make a prediction what's the product it could be, right? If this is a synthesis reaction, then you're gonna have only one product. If this is combustion reaction, they're going to generate CO2 or water. But this one, they are 2 ionic compounds. Okay, and we talk about if they have a 2 ionic compound, they must be a double displacement reactions. Must be double displacement reactions, which means the cation will switch to each other's. But once you're making a correct formula, you need to make sure what is the formula it will be. So now you can write like here, we have potassium, we have a phosphate, and we have an aluminum ion and a nitrate ion. So now we have 3 ions, and the 2 cation will switch the position. So the potassium ion will combine with nitrate, and aluminum ion will combine with the phosphate. And again, we said the cation always go first, anion go later. So potassium will combine with nitrate. You see, potassium is +1, nitrate is -1. So obviously they're going to making potassium nitrate ions. And then aluminum is +3, phosphate is -3. So obviously you're going to making aluminum phosphate like this, right? Yeah. And since you have those 2 are the correct formulas, please do not follow what those original formula shows, okay? Because you need to balance this equation, okay? You cannot write K3 N3 NO33. We do not have such formulas, okay, for the potassium nitrate. You have to make sure you write the correct formulas, and then you balance this equation. Yes.
So with the aluminum phosphate, does that have on the right side of the equation, does that have a 3 outside of the phosphate parentheses? On the very right side.
We don't have, look at here. Aluminum has 3 positive charge. Phosphate has a 3 negative charge.
Oh,
So,
okay, I didn't see that. Okay.
then those 2 combined together will be just like aluminum phosphate. Okay, yeah, so that's why once you write this correct formula, you need to make sure what's the charge for each of the cations or anion. Then you make a correct formula, right? Yeah, so those are the ionic compound. So based on the charge to determine what kind of formula it will be.
Okay, so now you write those two, and then make sure, okay, which one is the precipitate? So obviously this is precipitation reaction. Which one will be insoluble? If it's insoluble, then that's gonna be a precipitate. We talk about the rule. If 1A group of the 1A group metal plus any of the anion will be soluble. Potassium in the 1A group, so this guy should be soluble, okay? Or nitrate plus any of the cation will be soluble. So potassium nitrate definitely will be soluble. So this guy is soluble. If it's soluble, you're not write S. Okay, S means solid, not a soluble. So you write aqueous means this guy dissolving the water. And then aluminum phosphate should be a solid. If you're not sure, you can double check the solubility chart. Phosphate will be in the back column. You see the phosphate, and then you see the cation. Cation, they have a two category over here. In the top category, there's no aluminum ions shows up there, which means the aluminum belongs to the other ion. So the phosphate plus any other cation means low solubility, which is insoluble. Okay, so this is why you know aluminum phosphate is insoluble. So that's going to be a solid in the solution. Okay, which is a precipitate. Okay, this is how you predict the chemical reactions. Okay, very, very important. Okay, yeah, this is a very fundamental parts for the chemistry. And then the question is not just helping want us to write this, it's want us to write the net ionic equation, which means we need to rewrite those as a complete ionic equation and then make sure what is the net ionic equation, right? We first write the complete ionic equation. And again, so we say only those soluble compounds will be rewrite as a cation and anion, right? Because we said only the electrolytes is soluble in the water and generates the cation and anion. The insoluble parts is not going to. So only the one, those solids, when they dissolve in the water, they generate, there are no more potassium phosphate. Instead, they're only just the potassium ion and the phosphate ion. Okay, I already mentioned that several times. Okay, hopefully you listen that familiar. Okay, so now we're gonna rewrite those as a cation and anion. So we know potassium phosphate containing potassium ion and plus the phosphate ion. Well, but the thing is, yeah, I need to balance this equation first. So we're gonna put a 1 over here and put a 1 over here and 3 over here and 1 over here. Okay, so this one is balanced. Then if you look at it, if we have a 1 potassium phosphate, then we should have 3 of the potassium ion and a 1 phosphate ion. That makes sense, right? For the 1 of the aluminum nitrate, what are we gonna write? Yeah, so we should have 1 of the aluminum ions and plus 3 of the nitrate. Okay, I saw students, they write a nitrate ion, they write like this. Okay, there's no such ions. We only have a nitrate ion. The reason we put a 3 over here, that means we have a 3 of the nitrate. Okay, so the 3, for the 3 of the nitrate ion, we put a 3 in front. The reason we put a 3 over here, that's because those are the formula, right? This is one of the aluminum nitrate formula. I mean, you cannot write like aluminum 3 nitrate, right? we're not writing like this, right? So the 3 as a subscript for the 3 of the nitrate, we write like this. We're not writing 3 nitrate like this. So but if you only just have a single nitrate ion in the solution, then the nitrate, this is nitrate. And when you talk about 3 of nitrate, then the 3 put in front, okay? And then we're having 3 of the potassium ion and plus 3 of the nitrate ion. And the last one, aluminum phosphate. Aluminum phosphate is a solid, okay? This guy is a solid, which means they're not going to dissolve in water, so they're not going to become ions. Only the one can dissolve in the water, you're gonna write ions. This guy is a solid, which is not going to dissolve in water, so we will write this as it is. Okay, this is, I'm not sure how many times I already mentioned that, but I need to repeat it, repeat it, repeat it, and repeat until you remember it. Okay. So this is the purpose. Okay. Yeah. And you can think about, if you rewrite this as ions, then what happens? You're gonna have aluminum ions and you have the phosphate ions. If you write those as ion, what happened? Then you realize, wow, we have 3 potassium, 1 phosphate, 1 aluminum, 3 nitrate, 3 nitrate. Right? If you rewrite this as an ion, then you're gonna cancel everything. Then why we need to write this equation? Right? It doesn't mean anything. It's just because this guy is a solid. They're not going to making a cation and anions. So that's why we can write a chemical reactions or net ionic equations out there. So you will see this is a complete ionic equation. Then you will see, okay, potassium nitrate. We have a potassium and a nitrate. So potassium nitrate, those are the spectator ions. So you cancel those spectator ion. The leftover is just a phosphate ion react with aluminum ion. Then they're going to form aluminum phosphate solids. That's it. Okay, yeah. So at least in the net ion equation, you always have some left over. If there's no left over, then we don't have these equations. And if you look at the net ionic equation, you will realize the charge is balanced. So 3 positive charge, 3 negative charge, and then on the right side, we have a 0 charge. So the charge is balanced, and each of the elements is also balanced. So this is what happens in the net ionic equations. Okay, yeah. All right, I give you some a little bit time. Work on the question number 5. Go ahead. Page 15, question number 5. Then you probably need a solubility chart.
Okay, so let's review this. Okay, again. If you want to write a correct formula for the product, you have to recognize what the kind of cation and anion for each of the species. This is the first step. So first one, chromium nitrate. What are ions over there? So definitely we are going to have a chromium ions and the nitrate ions. We know nitrate has negative charge, but this chromium, what kind of charge for this chromium? Cr nitrate 3, right? We have 3 nitrate to balance one of the chromium. So how much charge for the chromium? Definitely is a 3 positive charge, right? Okay. So that's why I'm saying for a lot of the polyatomic ion, the common one, you're gonna remember it. If you don't remember, you're gonna take a long time to recognize what's the charge for those cations or anions. That you're gonna spend quite a long time. We talk about nitrate is one of the very common phosphate, carbonate, and sulfate. Those 4 polyatomic ion very common. NO3 minus, SO4 2 minus, CO3 2 minus, and PO4 3 minus. Those 3 polyatomic ion very common shows in the chemicals. So based on the charge, you should be able to figure out what is the charge for the cation. Okay, so this is a 3 positive, this is a, and then we have a potassium ions and the carbonate ions. Okay, so now you will figure out, okay, what kind of cation anion in this species, and then you just need to switch the position, right? The chromium will switch the position with the potassium. So potassium and the nitrate will combine together. Chromium and carbonate will combine together. So in this case, they are going to generate potassium and nitrate. 1 positive charge, 1 negative charge. So you're going to have a potassium nitrate. So this is one of the compounds. The other is chromium 3 combined with carbonate. So this is 3 positive charge. This is a 2 negative charge. Okay, based on the formula, you write what's the formula will be. 2 go underneath over here, 3 go underneath over here. So Cr2, C33, CO33. So that's gonna be a formula, right? And you see potassium nitrate is aqueous because this guy is soluble. 1A group plus any of the cation will be soluble. Second one, this is a insoluble compound. If you look at the solubility chart, you see this is insoluble. So that's why we're making a correct formulas. And then you balance the equations. So we assume this one is 1. So we're gonna definitely have 2 up here. So we have 3 carbonates. You're gonna put 3 carbonates over here. And we're gonna put 6 over here. And this equation is balanced. Okay, yeah. And then you rewrite this equation to a net ionic equation. And you see 2 of the chromium nitrate. Then how many chlorine ions we have? How many nitrate ions do we have? So definitely this guy have a 2 of the chromium ions. And since we have 2 times 3, we have a 6 nitrate ion over there, right? We're going to have a 6 nitrate ions over there. So this is from the first one. Second one, we have 3 of the potassium carbonate. How many potassium ion we have? How many carbonate ion we have? Potassium, we have a 6 potassium ion. And how many carbonate? We have 3 of the carbonate. C, 3 of the CO3 2 minus. Remember, don't forget the charge. The charge very important because the charge shows off there means those are the polyatomic ion. Those are ions. Okay, those are not of molecules. And then we're going to separate this 6 potassium nitrate means we have a 6 potassium ion and 6 nitrate ions. And we are going to have a 1 chromium 3 carbonate. This is solids. Okay, so this is what we call the complete ionic equation. And if you're talking about the spectator ion, the 6 of the potassium and 6 of the nitrate, those are the spectator ion. So you can cancel those. And the left over is just 2 of the chromium ions plus 3 of the carbonate ions. And then they are going to form a chromium carbonate. So again, what's the meaning of this? That means nitrate and potassium is not doing anything in these reactions. They're really doing the reactions. The thing is just a chromium and a carbonate. Those two combined together make up precipitate, and that's it. Okay, yeah. So this is yeah, we spent like half an hour on what we learned last time. Okay, let's take a break, and then we will talk about stoichiometry.
This is 2.0 that I wasn't able to connect up to the last class. I got the prelim questions and all the. Yeah, I think I see that part, and then I'm working on the lab questions for tonight. Not yet, I'm gonna do that after class today. Yeah.
why. So this is one of the ways to modify. Once you run the nodes, modify as small as the node of this, and then it does the ratios. No, precipitation is a solid, and then individual, we talk about ions. If you can write ions, then it's got a solution. It shouldn't be a precipitate. Precipitate is a solid. It's out of the solutions. Which means they have to be by a anion and by together making a compound. Okay, so like other this is that's a precipitate, and this is actually we write this as a but actually the solution is actually is passing on antibiotic ions. Okay, but this one is a precipitate. It's coming out of the solution. You cannot write this as that ion and chloride because they're not dissolved in water. Only dissolved in water, you're going to write ions. So that's the concept. So we're asking for precipitate. Then just write the solids. Which one is solid? Okay. Which one is insoluble in the solution? Then that's a precipitate. So now, they have solid acid above. This is not a chlorate. If you look at the polyatomic, this is chlorate, right? What's the charge? -1. What is the potential charge? +1. So what is the formula? +1 and -1. So just one potential ion combined with one of the chlorine ions. Exactly. ClO3 is a polyatomic ion. There's a whole molecule. All things have a one atom charge. Yeah, so this is one, and then you look at here, what they make. They make a solid potassium chloride. I don't think this is potassium chloride. That's the chloride. What is a chloride? The chloride, this is called chloride. This separate. Okay, they are making solid potassium chloride and oxygen gases. Oxygen gases is O2, not O. Eventually, we know this. Hey guys.
Okay, so the next part, we're going to talk about the stoichiometry. Just so you know, stoichiometry. We're going to use the stoichiometry not just in this unit. It's going to use in the unit 2, in the unit 4. Okay, so this is the fundamental concept in chemistry. Okay, a lot of calculation is coming from the stoichiometry. Okay. So generally, let me just talk about what exactly is the stoichiometry. Stoichiometry looks like it's pretty complicated, but actually it's pretty easy. Well, the thing is, you can think about the stoichiometry as like making food. It's a recipe of the food. You can assume one of the chemical reactions is a recipe of the food. For example, okay, so let's just making a hamburger. Okay, so let's think about, okay, when we make a hamburger, what do we need?
We need 2 of the bombs. So that's a bomb, okay? 2 bombs. We have 2 bombs. And then you're having a steak, right? Okay, so we're going to have a steak. So we have 1 steak. And then what we have?
2 cheese. 2 cheese. Okay,
Actually, I want the triple cheese.
okay, triple cheese. Okay.
What I thought.
Okay, and then let's be healthy. We got some letters. Okay. Wait, how to spell the letters? UCE. Okay, 2 letters. Maybe too much. I don't know. Well, and then we're going to put one of the. Let's see, what's this?
Tomato.
Yeah, tomato. Okay, we put some of the tomato. 1 tomato over here. All right, so then we should be able to making a hamburger. Well, probably it's a Big Mac. Okay, so it's really big. Okay, so this is a Big Mac. All right, so now what you make here is just a recipe, right? As long as we follow this recipe, we can making the food. Okay, yeah. So stoichiometry is the same thing. You can assume one of the compound, the chemical reactions is just a recipe. And so here, what exactly is the stoichiometry? The stoichiometry question is asking for example, if I have 100 bombs and I have unlimited the rest of the other recipes, okay? If I have 100 bombs and I have unlimited other stuff, and how many
of the Big Mac can we make?
If we have only 100 bombs. You know, should be 50, right? You can make a 50 Big Mac. But think about how do you make it? How do you see? How do you calculate this? First of all, you need to find the coefficient, the link between how many bombs to making how many Big Mac, right? So 2 bombs should equal to 1 Big Mac. So this is your first thought, okay? Yeah, although you already calculate this in your mind, but this is the first thing you find. You find the relationship between the bombs and the Big Mac, okay? 2 bombs, 1 Big Mac. And we know we originally have 100 bombs, okay? And then you just need to multiply the conversion, the unit conversion, since 2 bombs equal to 1 Big Mac. You're gonna 2 bombs and 1 Big Mac. And think about why we put the bombs in the bottom, why we divide by 2 instead of multiply by 2. That's because the bombs need to be canceled, right? And then we got a Big Mac. So that's why you have a 50 Big Mac. Well, this one then maybe is easier. Then another question is, so if I have like a 58 bombs, and also I have how many cheese do we need that we can use up all the cheese and the bombs? Then what we can do? I mean, maybe you need to twist a little bit mind to calculate, right? And so that's why sometimes you cannot just do the calculation in your mind. You need to set up an equation to solve the problem, right? So now we have a 58 bombs. How many cheese that we need to use up all the bombs? And how do we set up? Well, what we have? First, you need to find a link between bombs and the cheese, right? 2 bombs, that's equal to 3 cheeses, which means we use up 2 bombs, then we're gonna use 3 cheeses. So what we have is 58 bombs. And then you multiply something and divide by something to get the cheese. So obviously you need to cancel the cheese. So when you cancel the bomb, when you set up this equation and put the coefficient in there, you need to set up this equation. Which one we need to put? Do we need to divide by the 2 or do we need to multiply by 2? So that's really depends on where you set up this, because we want to cancel the bomb and we want to get the cheese. So in front of bomb is 2, so you put 2 up here. In front of cheese 3, that's 3. You put 3. So that's why you need to divide by 2 and multiply by 3. So bomb canceled. If you write this equation, it's just a 58 multiplied by 3 and divide by 2. So this is a 29 times 3. 87. Okay, and this is 87 cheeses. You got it? This is the stoichiometry, is it? Not that hard, right? Okay. So we can just use the same concept, just do one of the stoichiometry. Let's look at the page. Let's say the page 18. Question number 1. Okay, so for this question, page 8, question number 1. We have this is C8, right? Yeah, C8H8. This compound react with oxygen to, this is a combustion reaction, you see? They react with oxygen to produce water and CO2, okay? So they're asking for how many moles of water will be produced if 1.2 moles of oxygen is reacted with excess. Oh, sorry, this is C3H8, not C8H8, C3H8. So this is propane with excess propane. Excess means it's unlimited or extra. Okay, so you don't have to worry about this guy is a limit to the reactions. So first of all, you need to balance the equation to find out the coefficient, of course. Yeah, right. So you put 1 over here. And then we're going to have a 3 CO2. And also we have a 4 of this. And then you calculate the oxygen, 4 plus 6, so 10. We'll put 5 on here. So that's going to be the coefficient. Then you look at it. Here we are looking, we have oxygen. So we have oxygen. And what we're looking for? We're looking for water. Okay, so they have water. So now first thought, it's just like if if I have the bombs, how many Big Mac we can make? So first, you need to find the relationship between the oxygen and water. So now the 5 oxygen will equal to 4 water, right? This is set up. And the coefficient here is also, those coefficients you can think about as a single molecule ratio, which means 1 propane molecule react with 5 oxygen molecule will react to form 4 water molecules and 3 CO2 molecules. You can also think of this as a mole ratios, which means 1 mole of the propane react with 5 moles of water will form 4 moles of react with 5 moles of oxygen to form 4 moles of water and 3 moles of CO2. So those are also the mole ratio. So you can think about this is if we use up 5 moles of oxygen, we're going to generate 4 moles of water. Okay, so this is the relationship. All right, then that's it. What we have 1.2 moles of the oxygen. And then you set up, you try to figure out the water. Then where you put the oxygen? Well, obviously you're gonna put the oxygen in the bottom, right? And you're gonna put the water on the top. So in front of water is oxygen is 5, so you put 5 up there. In front of the water is 4, so you put 4 there. And obviously oxygen canceled. Now left over will be just more of the water. Will be just more of the water. So when you set up, do the equation, it's just 1.2, you times 4 and you divide by 5. And then you got more of the water. This is a 4.8 divided by 5. The answer will be just 0.96. More of the water. Make sense, right? Pretty straightforward, right? Yeah. Well, let's just do one more thing. So the equation that's going to be important. Okay, you need to base on the equation to find the coefficient. No coefficient, no calculation. Okay, no stoichiometry. Okay, so the next one again is that how many moles of potassium are needed to react with 0.633 moles of the mercury to chloride. Okay, so now we have a potassium and we're looking for the mercury chloride. So we need to find the relationship between this. To set up this equation, then I said, okay, to balance this equation, better find chemicals that has multiple elements and has the biggest numbers of the elements. So that's why I'm assume this one is a 1, because this one has
two elements in the compound, and also chlorine has two over there. Okay, so I assume this one is 1. That means we're going to put a 1 in front of mercury and put a 2 for the potassium chloride, because we have two chloride ion. So put a 2 up there. And then you can see, okay, we're gonna put a 2 for the potassium. Then this equation is balanced. So now what we have is 0.633 mole of the mercury 2 chloride. And we try to figure out the mole of the potassium. Okay, so the relationship between the mercury and the mercury chloride and the potassium is 1:2. So this guy, what we have is mercury. So when you set up, obviously you're gonna put the mercury 2 chloride in the bottom and put the potassium on the top. Okay, so in this case, mercury can be canceled. Then if you look at the coefficient, in front of mercury is 1, so you put a 1 over here. In front of potassium is 2, so you put a 2 over here. Okay, so mercury canceled. So that's why you will know this equation is just 0.633 times 2 divided by 1, right? And so that's why the answer will be 1.27. 1.27. You got it? Okay. Yeah. So this is how we figure out the stoichiometry. Pretty straightforward, right? Okay. So go ahead to work on the question number 8. Okay. Go ahead to work on the question number 8. And again, you're gonna balance this equation, okay? So to balance this equation, again, we talk about, you're gonna looking at the sum of the compound, has a multiple elements and has the highest number shows in the molecules. And then you assume this compound is a 1. So if you look at over for all those elements, compounds, definitely the first one has multiple elements and also has the highest number shows over there. Okay, so we assume this guy is a 1. And then we have a 1 lead, which means we can put a 1 over there. For nitrate,
So we put 4 up there. And then you will realize we're gonna have a 4 for this, and this is the coefficient, okay, between each of the element compounds. All right, so here is asking for how many of the lead-4 iodide. So we're looking for lead-4 iodide, and what we have a sodium nitrate. So sodium nitrate. That means we generate 11.7 moles of sodium nitrate. How many moles of lead iodide that we can produce? Well, so you set up, we have 11.7
mole of the sodium nitrate. And then you multiply, definitely gonna cancel the moles of nitrate. And then you multiply the moles of the lead iodide. In front of lead iodide is 1. In front of the sodium nitrate is 4. Okay, so now you know this canceled. You will know it's just 11.7 divided by 4. Okay, so the answer will be 2.93. 2.93. You got it? Okay, so this is the what we talk about. This is a backbone for stoichiometry. Okay, the reason in the future, Unit 3, Unit 4, we're going to still using stoichiometry. Even in the lab, we're going to using stoichiometry. That's because stoichiometry, they do have different kind of the variation. But the fundamental parts is just a mole to mole ratio. So that's why this kind of stoichiometry we call it as a mole to mole ratio stoichiometry. The reason is because we're using mole of the sum of compounds to figure out the mole of other compounds. So this is called the mole to mole ratio stoichiometry. And this is a backbone, okay? And this is a fundamental for stoichiometry. The reason later we are going to have a variation, that's because, for example, in the lab, can you measure, I'm asking you to measure 0.5 moles of the sodium chloride. Can you use any of the device to measure 0.5 moles of sodium chloride? No, you can't, right? What you can measure? You can measure the mass of sodium chloride, right? Okay, so you have to convert the mass of the sodium chloride to the mole of the sodium chloride, or you convert 0.5 moles of sodium chloride, multiply the molar mass, then we got the mass. So you know how much mass of the sodium chloride you can measure to get 0.5 moles, right? Yeah, so the same thing. So that's why when we do the, I want you to measure 1 gram, 1.0 gram of sodium chloride. And then we're doing some of the experiments. And you're gonna figure out, or this one, okay. I want to measure 1 gram of the sodium iodide in this experiment, okay? And then I want you to figure out how many moles or how many gram of the lead-4 nitrate that we need to make all the 1 gram of the sodium nitrate iodide is completely reacted, okay? But in this case, we're not having moles over there, but you see the backbone here is mole to mole stoichiometry, which means you have to using mole of something to figure out the mole of the other things, right? Those ratio is moles, which means if I measure 4 gram of the sodium iodide, we're not going to just, we cannot using 1 gram of the lead nitrate to complete use up, right? This is the mole ratio. Those are 4 versus 4. 1 versus 4 is the mole ratio. It's not the mass ratio. You have to convert the mass to the mole and doing the calculations. Okay, so that's why we have the variation. And the next part, we're going to talk about the variation. The variation is called the mass to mole, mole to mass stoichiometry.
Okay, so let's look at one of the questions shows over here, okay? The first one here, it says the amount of the chloride ions in a water sample is to be determined by adding excess silver nitrate. 1.0 gram of the silver chloride is precipitated. What is the mass of the chloride ion that is originally in original sample? So first, let's set up the equation. What we have is we have a chloride ions in the solution, and then we're adding a silver nitrate in this solution. And then they are going to making a silver
chloride precipitate. And then could you tell me what's the leftover in this equation? What's the leftover in this equation?
nitrate ions. That's the leftover. All right. So now this is the setup for the equations. Then what the question asking for? They asking for what is the mass of the chloride ion? And what we have? We have 1.0 gram of silver chloride, which means we have 1.0 gram of the silver chloride. And we try to figure out the mass of the chloride ion. So again, that's gonna be what we call the mass to mole to mass stoichiometry. So let me just rewrite this over here. So what we have 1.0 gram of this, and we try to figure out the mass of the chloride ion. So now, every time when you do the stoichiometry, especially like this, I recommend you draw a pathway to solve this question. Okay, draw a pathway. So think about, and since the stoichiometry, the coefficient, I think this is already balanced. This is just 1 to 1 to 1 to 1. Okay, so everything is 1. So we solve this problem since the coefficient 1 to 1 here is the mole ratio. Okay, it's not the mass ratio. It doesn't mean we have 1.0 gram of silver chloride. We're going to generate 1 gram.
We should have 1 gram of chloride, right? This is the ratio 1 to 1 here is a mole ratio. 1 mole of this will generate 1 mole of that. It's not 1 gram of this generate 1 gram of that. So once you do the stoichiometry, you have to convert mass to the mole. So first, the first thing is we need to find how many moles of the silver chloride we have. That makes sense, right? And then we base on the stoichiometry. This is 1 to 1 ratio, so we got moles of the silver chloride, and then we will be able to figure out what is the mole of the chloride ions, right? And once you have the mole of the chloride ions, again,
this is a callback to the beginning of this unit too. How to convert the mass to the mole, how to convert the mole to the mass. Okay. Yeah, so mole to the mass, you just need to multiply the molar mass. Okay. You multiply the molar mass, you got the mass. Mole multiply molar mass, you got a mass. Mass to the mole. It has a mass, you're gonna divide by the molar mass, and you got the mole, okay? So that's why I hope you're gonna remember the equation. Mass over molar mass equal to mole. Mole multiply mass, molar mass equal to mass. Okay, so that's gonna be the step. And if you calculate it, how many steps do we have? First step, second step, third step.
So in general, when you solve this problem, you suppose has a 3 steps to go. Okay, so that's why let's look at it. First step, you're gonna convert the mass of the silver chloride to the mole of the silver chloride. This is the first step. Okay, so that is why we talk about stoichiometry. That's mole to mole ratio. So the key is to find a mole of something. Okay, key is to find a mole of something. Otherwise, you cannot otherwise you cannot solve the stoichiometry. You have to find the mole of something. So mole of the, okay, since we have a two different compound, then you need to make sure what you have. You have a mole of the silver chloride. Then that should be equal to 1.0 gram of the silver chloride divided by the molar mass of silver chloride. The question already telling us the molar mass of silver chloride is 143.25. 143.25. This is gram per mole. And you have, okay, put it into your calculator. 1.0 divided by 143.25. For these cases, I recommend you keep long enough sig fig for the calculations, okay? It's a sig fig, not keep decimals, okay? So in this case, you at least you're gonna keep four sig figs. So 0.006981. This is a mole of the silver chloride. Okay, so now once you got a mole of silver chloride, then you should be able to, based on the stoichiometry, to figure out mole of the chloride ions. Remember, we just did that. How did we do this? (1:1) ratio, right? So if you have a, this is step 2. You find a mole of the chloride ion. Then that should be mole of the silver chloride. We have is 0.00698 mole of the silver chloride. And then you multiply the coefficient. You're gonna cancel the mole, 1 mole of the silver chloride, and put 1 mole of the chloride ion up there, since this is 1:1 ratio. So the silver chloride is canceled. Now, since this is 1:1, which means the mole of the silver chloride is the mole of the chloride ion. So you have 0.00698 mole of the silver of the chloride ion. Okay, so this is step 2. Then the last step, this is going to be convert the mole of the chloride ion to the mass of the chloride ion. Okay, so what we do, 0.00698 mole, 681 mole of the chloride ion. Mole multiply molar mass to got mass. Mole multiply molar mass to got mass. The molar mass of the chloride ion is in the periodic table. This molar mass of the chloride ion. So that's 35.453. 35.453. A lot of people, they may think about, okay, the mass of the chlorine and then the mass of the chlorine ions, is there a difference? I'm telling you, generally, there's no difference between those two, okay? Because the electron's mass is really negligible, okay? Yeah, so generally, you don't have to worry about the mass of the chlorine, the mass of the electrons. So those two are the same, okay? So that's why you time the molar mass of this is gram per mole. Then you will figure out the mass of the chlorine. 0.247. Okay, 0.247. And this is in gram, okay? And then if you look at a sig fig, the question only gave us just one number. The molar mass will not count for the sig fig, okay? Only just 1.0 gram. So the question gave you just two sig fig. So you're going to keep two sig fig. So the answer will be 0.25 gram. Okay, 0.25 gram. That's it. Okay, so you're going to have several steps for the stoichiometry. Okay, several steps for the stoichiometry. And to be honest, if you go faster, okay, if you're familiar with later, after some practice, if you're familiar with this step, you can combine the 1, 2, 3 steps in one equation. Okay, just combine everything together. So I'm going to write down the combined equations. Okay, combine the equations. So you can set up a long equation over here. What we have is beginning, we have 1.0 gram of the silver chloride. This is what we have. And then you're going to divide by the molar mass, right? You divide by the molar mass. So you just write divided by molar mass of this, which is 143.25 gram per mole. If you write like this, that's fine. Okay, if you want to write one of there, that's fine. Or even you don't have to write anything. Okay, that's totally fine. Okay, so and then once you're done this, you go to the next step. You're doing stoichiometry. So here is a silver chloride. So we're going to cancel the silver chloride. And what we got? We need to get the chloride. And if you look at the coefficient, that is a 1-to-1 ratio. So one silver chloride got one of the chloride. This is second step, which is the stoichiometry part. And then after that, you're going to have a mole. You multiply the molar mass of the chloride, which is 35.453 gram per mole. This is also fine. So you will see silver chloride canceled, gram per mole canceled. Okay, and then the leftover is just in gram of the chloride ions. So if you set up this equation, and the leftover, you can see just a 0.0 times 1 times 35.453 and divided by 143.25 times 1. And then if you're doing this, you're still going to have the same equation, the same result. 1.0 times 1 times 35.453 divided by parenthesis 143.25 times 1. You see, the answer is still 0.247. Okay, yeah. So you can combine this together to write the equations. That's totally fine. Okay, yeah. This probably will save your time while you're doing calculations. Okay, yeah. So we definitely will do more practice for the stoichiometry, and I will assign the homework for you for the stoichiometry. Okay, yeah. Okay, so now go ahead to got the study guide. I'm going to assign the homework. And by the way, I need to mention one thing is, okay, so today is Thursday, right? And the next week, we're still going to have a lecture. And then we're going to have an exam on 7th. Okay, we will have an exam on 7th. So 28th, we will have a quiz, right? And we talk about the quiz is writing the chemical reactions. Give you a reactant, and you're gonna predict what is the product it will be. Okay, totally, we only have 4 questions, 4 chemical reactions. Give you the reactant, you're going to predict what is the product. Okay, yeah. And three this kind of reaction, and one of the reaction, you're gonna write down what is the ionic comp and the net ionic equations. Okay, yeah. So that's what we're gonna to test on the 28th. So and the next week, we're not going to have a lab. Instead, I'm going to use the lab time to work on the practice. Okay, so you just doing the practice on over here. Okay, yeah. So just like what we did in the unit 1. Okay, yeah. I spent 2 days to work on this. Very important. There's a lot of the concept and a lot of calculations. Okay, yeah. So to be honest, unit 2 is the fundamental parts for the chemistry. Okay, fundamental parts for the chemistry. Okay, and then we will have the exam on 7th. Okay, yeah. Okay, so let's turn to the turn to page 13. Turn to the page 13. And then let's look at, okay, so question number 2. I think it's better to write this down. Okay. Number 2. Number 4. Number 8. Number 9. 12. 15. $16. Page 16. 6. And 9. Okay, page 18, 9, and 10. All right, so those are the first part is give you a compound and try to predict what is the result, what is the product. Okay, so when you're doing this predict, first look at what is those chemicals. If the both are ionic compounds, then definitely it's a double displacement reactions. If there's only one compound for the reactant, then definitely it's a decomposition reactions. If they are having oxygen and a hydrocarbon, then that's a combustion reactions. Okay. If they have one single elements and one ionic compounds, then that's a single displacement reactions. Right? This is what we talk about. Again, if you do have any questions, send me email. I will help you out. Okay. Yeah. Well, better to think about on your own first. If you spend like half an hour, have no clue, send me email for sure. Okay, yeah. And or you can take a picture of this. I'm going to just record my my notes and send that back to you. Okay, yeah. Okay, so let's pack up things and we will move to the lab.